So we know that sampling-based motion planning is an effective tool for solving many kinds of planning problems, including kinematic planning, as well as planning under differential constraints. And so, an example would be this Stubbins car or any of the examples the previous speaker brought up. But these sampling-based methods still struggle with piecewise analytic differential constraints. And as a brief reminder, a piecewise analytic differential constraint is a constraint that's analytic on each of a finite set of manifolds, which we're going to refer to as modes. And so to give you a sense of what this actually looks like, if you have a problem with piecewise analytic constraints, somewhere in your code, there's going to be something that looks like a switch statement or a chain of if-else that tells you, for a given state and control input, which kind of dynamics are we in right now. And this shows up in many different planning domains. So a lot of things that are often thought of as task and motion planning domains, like rearrangement planning or object manipulation, as well as things that are normally thought of more as motion planning, like legged locomotion. And so because this is such a common set of dynamics, it's been very well studied, but most of the prior research has focused on satisficing planning, finding any plan that accomplishes the objectives of the plan, and relatively little is focused on optimal planning, looking for both a solution that accomplishes the goal and minimizes some cost function. And so in this work, we develop a pair of algorithms that are both provably asymptotically optimal under fairly mild conditions on the problem domain. And so in order to motivate this algorithm, I'm going to work with a very simple toy problem, not because it's particularly interesting, but because it is a two-dimensional configuration space, and so I can draw it on the slide. We've got two robots that are constrained to move on a ring. There's a red one marked R for robot, and a blue one marked O for other robot, because I'm not good at naming things. The gray areas in this configuration space are the configurations where the robots would be in collision. You have to imagine the left edge and the right edge are glued together, the top edge and the bottom edge are glued together, so this is a flat torus. And so an example of a simple task you might ask these robots to do is to switch places. And there's two optimal solutions corresponding to the two directions robots can move. I've drawn one of them here, where the red robot loops all the way around, the blue robot takes a short path, and in configuration space, that involves looping around the left edge and coming back to the right edge of the graph. And there's many ways we could find a solution to this planning problem. I've drawn two on the board here. On the left is a PRM star, on the right's a fast marching tree. But the point is that this isn't a very difficult problem. And that's because the locally reachable set is always going to be a manifold. And so we can easily solve the two-point boundary value problem. But let's say that one of the robot's batteries die, and we still want to accomplish this task. And so the red robot now needs to push the blue robot into position. And so the blue robot can only move when the robots are in contact. And now the shortest path has gotten quite a bit longer. So here's what it looks like in configuration space. The red robot has to loop around, approach this low-dimensional contact manifold, slide down it, getting the blue robot into position, and then back off. And so this is obviously a more complex path and a much longer path. And what's going on here is that these dynamics are piecewise analytic. When the robots are not in contact, we have an analytic dynamical system for which planning is relatively easy. But when the robots make contact, we enter a new dynamical system. And again, this is another analytic dynamical system. Planning is still easy. But these dynamical systems are different. Neither one of them is locally controllable. And we can reach different parts of the local configuration space depending on which mode we're on. So this is a system that is globally controllable, but neither mode is locally controllable. And the important thing is that they are locally controllable in different ways. And so just a little bit more terminology. We're going to refer to the set of states that we can reach without leaving a mode as an orbit. Orbits will always be manifolds, thanks to both the piecewise analyticity and the Frobenius theorem. And so I've just drawn a few orbits up here. On the right, you can see that a configuration that lies on the intersection of two modes will actually have two different orbits. And so what's interesting is that if the orbits are low-dimensional, if there are directions in which we can't move, then in order to move between two configurations, we may need to switch modes. And that means that the shortest path between two arbitrarily close points in configuration space can be arbitrarily long. And that's the core of the problem with applying sampling-based algorithms to piecewise analytic domains. Many algorithms can rapidly explore a single orbit, but most sampling-based algorithms will be either incomplete, suboptimal, or inefficient if you ask them to explore across different modes. But if we always restrict ourselves to a single orbit, then exploration will always be fast. And if we make sure to sample from the intersection between modes and to only consider connections between points on the same orbit, then we can get rapid and asymptotically optimal exploration across the entire configuration space. And so that's really the insight behind our algorithm, which we call the orbital Bellman tree. Orbital because we're planning across orbits. Bellman because we're going to use a Bellman recursion in order to build up this tree. And so the first step is we take our initial configuration, we sample from the orbit containing it, both making sure we include samples from the interior and from the intersection of that orbit with the adjacent modes. And we make sure to, so then we create an edge between each pair of samples that's less than some critical distance. And you might notice that this looks an awful lot like the critical distance for something like an ROT or a PRM. There's an extra factor of 2 in there. That comes from the fact that we're going to be exploring a sequence of orbits that has to be close to an optimal sequence, but it won't be exactly an optimal sequence. In this case, creating an edge means building a spatial index of some kind, like a KD tree. And we're going to be building a new KD tree for each orbit that we explore. And observe here that the dimension d in each of these equations is the dimension of the orbit, not of the configuration space. And likewise, the measure of free space is the measure of the orbit. And that's going to let us use a much smaller radius of connectivity. And so our approach is to repeatedly expand vertices in a best first fashion, using something like A star. And when we expand a vertex, what we need to do is make sure that any orbit containing that vertex has samples, both from the interior and from the intersection with any adjacent modes. And then we will try and make connections to all the neighboring orbits, put them on a priority queue, and iterate until we find a path to the goal. And if we do this long enough, we'll eventually densely sample the configuration space. And what we can show is that we will get good paths to everywhere in the configuration space. And there's two nice things about this setup. One is that we only have to consider neighbors on the same orbit, which means exploration is fast. And the second is that the requirements for our local planner are very weak. We don't have to ever consider the possibility that we're going to have to plan very long trajectories to move between orbits. We can actually use things like simple straight line planners in quite a few situations. And so what we can guarantee is that we'll almost surely find an optimal trajectory in the limit of infinite samples on each orbit. More concretely, we will find a near optimal trajectory with high probability if the number of samples is high enough for arbitrary definitions of near optimal and high probability. And the conditions under which this hold are fairly mild. So we do require that the problem geometry be a manifold. We require that dynamics be piecewise analytic and that we know the modes. And we have two conditions on the local planner itself. First, we need to make sure that if 2 points lie inside an open ball of free space, then the planner will be able to connect them. And we can make that ball arbitrarily small, but this lets us connect to configurations that are on the boundary of each mode. Second, if the points are close enough, the local planner needs to return a near optimal trajectory. This is a relatively mild condition that ensures that if we eventually get enough samples, we'll be able to add them up to an optimal path. Both of these last two conditions hold for straight line planners as well as geodesic planners and asymptotically optimizing planners. Now, there's still some inefficiency here in that we're reconstructing a new spatial index on every orbit. And I don't have enough time to go into a lot of detail about why this works, but we can actually instead construct a sample only once, or construct a graph only once, if the dynamics have a particular factored structure. And that's a factored structure that's common in problems like quasi-static manipulation. And that lets us build far fewer spatial indices, which brings down the complexity into something that's much more manageable. So as an example of a case where something like this makes a lot of sense, we can talk about motion planning with movable objects. So here we have a triangular robot that's trying to move this red box into the red region. And there's a green box that's sort of on the direct path to the region, but there's another option. It could take this upper doorway. Right? So its goal is to minimize the total path length. And if we try and solve this with sort of a conventional hierarchical task in motion planner, there's a very simple plan that will succeed, which is to go up, go over, bring the box back down. But this plan is suboptimal. And so our approach will realize that there's actually a shorter but more complicated plan, which is to move the lower box out of the way and then grab the red box and take it directly through the doorway. So we did some quantitative experiments on this. This is the same planning problem run many different times with only two things changing. One is the random seed that we use to generate samples, and the other is the number of samples that we collect on each orbit. And so what we see is that with relatively few samples, we find good paths, generally better than the paths that we can find with a hierarchical motion planner. But it's a very computationally expensive process. The complexity scales here with the cube of the number of samples, and that's because there's 3 objects in the environment, generally be exponential with the number of objects in the environment. And so if we sort of plot these two against each other, we see there's a lot of variance in the quality of the path that's returned, and also that we get rapidly diminishing returns. And I didn't just arbitrarily cut off this graph on the right. We actually start to run out of memory as we get further over, and that's because we're exploring an exponentially large graph. But we are finding better paths with relatively few samples. So, in closing thoughts and dirty laundry, there's 2 major disadvantages here. One that I've sort of glossed over is that we need the ability to sample from orbits and to identify modes and to sample from the intersection between modes and orbits. And that's not always trivial. For something like manipulation, that's sampling grasping poses. And so for many problems, we can build that system, but there are cases where it'll be much more difficult. The second thing is that we are not making any use of abstraction. And that means that we're getting hit by the curse of dimensionality, trying to plan in this exponentially large space of configurations. And that's obviously problematic. We know that in the worst case, the problems that we're trying to solve are p-space hard, and so there aren't going to be generally efficient solutions. What we might hope for is that for an easy problem, or maybe in the average case, we can get solutions much more quickly. And so what we believe is that these 2 algorithms, the orbital Bellman tree and the factored orbital Bellman tree, will be useful building blocks for more general, asymptotically optimal task and motion planning algorithms. Thank you.
Thank you very much. Ross Nepper is our first responder.
Thanks. I really appreciate something about this paper, which is that you've effectively subsumed the task and motion planning problem into the motion planning problem. Very clever. Something I didn't quite get is, so you have to sample on the various different modes in order to cover the space, but you also have to sample in the intersections. And I saw in the paper that when you discover a new orbit that you've never visited, you sample both in that new orbit and also on that intersection or boundary between the two. But later on, I didn't see a mechanism where you'd come back and repopulate that. So effectively, you would revisit it with probability 0 due to it being lower dimensionality. So how do you actually guarantee asymptotic optimality across these boundaries?
Yeah, so one assumption that we make is that we're only going to transverse a finite number of modes on the way to an optimal solution. So you can't have Zeno phenomenon going on here. And so that means we actually don't need to guarantee that we get back to an orbit we've seen before in order to get asymptotic optimality. Now, what happens with the factored tree, and where being able to come back to the same orbit is very, very useful, is that if we don't touch an object, then we can reuse its graph every time, right? And so we're going to keep on coming back to the same orbits of some of the objects, maybe not all of them. And so that's really where the being able to come back to orbits is helpful.
Okay, all right. We have time for one more question. Okay, somebody's waving at the back, but I think it's you.
Yeah, so I work on self-driving trucks, and self-driving truck has different modes in the sense that there's multiple gears it can be in. But there you can choose to switch between modes. It's not an intersection per se, it's just, well, maybe you can also think of a large region of intersection, but you can basically at any point go up or down in gear, right? Mm-hmm. Would your method apply to that as well, or is that a completely different problem?
So that's actually not dissimilar from one of the transitions that you see in manipulation. There's only a few ways I can grab an object, but I can always choose to release the object. And so in a sort of a similar way with a truck, you can always choose to shift gears, subject to maybe some dynamic constraints. And so the ideas are certainly applicable. One thing we haven't really dealt with here, although there's no theoretical reason why we couldn't do it, is full dynamics. We're assuming everything is quasi-static. But if we were to work in phase space instead of in configuration space, I imagine that we could probably solve things like gear shifting as well.
All right. Okay, I think we can thank our speaker again.